So hello everyone, good morning and welcome to our presentation. Thanks for coming. We are Team MathWire, and for the past 4 months we have been working on the location awareness project. I'd like to introduce you to the team. I am Vieri, we have Roy, Lizzie, Hunter, and we have Robert, Tim, and Karani. So what is our project about? So imagine you're in a museum or an exhibition, and you can walk up to an artifact and you could be uniquely addressed with some feedback that's tailored to you. This could be your name, your language, and your interests. So that's what we're trying to aim for with our project. We want our visitor to walk up to a booth and be addressed uniquely with an audio-visual feedback. In our case, we can have a different language, address him by his name, and then eventually get his interest and give him a different feedback every time. So by doing this, we had to come up with a software and hardware complete package solution, keep the cost down, and also offer the minimum inconvenience, obviously, for the visitor. So the only thing the visitor has to do is wear a small lanyard containing an RFID tag, in which we store the data that we can later on access from a database to then obviously give a unique feedback for each and every one of our visitors. But let's go into a little more detail about our project. So our project is split into 3 main parts. We have a sensing part, a processing part, and then we have the presentation of the data. Our sensing part is split into 3 main parts, we can say. We need to know 3 main things about the visitor. We need to know where he is, we need to know who he is, and also we need to know if he's interested in the artifact or not, obviously. So how do we do that? Quickly, so the ultrasonic sensor is going to detect the distance from the visitor from the artifact. Then we need to know if he's interested, and we implemented that with a software solution with official detection software using low-cost cameras with a Raspberry Pi. Then we had to determine who the visitor was, so we're using an RFID system, including an RFID antenna, an RFID reader, and obviously the tags that the visitors are going to wear. With all this data we need to process, we needed 3 main elements and the processing part. So we have a PIC24 microcontroller, we have a Raspberry Pi, and then we have a backend database. So how does this work? Our data buffer gets the data from our sensors, so the ultrasonic sensor and the RFID reader, puts it in a packet that then gets sent to Raspberry Pi. So Raspberry Pi is the main processing unit, so it processes the data and queries a back-end database. It gets all the data, and then with that we can give a unique presentation through an audio-visual feedback through a monitor speaker setup. Once we do this, we can speak in different languages and address each visitor in a different way based on their preferences. So to talk a little bit more about the software side of things, I'm going to hand it on to Robert.
So for our software main processing unit, we decided to use a Raspberry Pi 2 because it's very cheap and it has actually a ton of processing power. So the Raspberry Pi will receive packets from our data buffer. The information will be contained as proximity data and a tag ID. We'll use the proximity detection to see if the user is maybe doesn't have their tag right and we can't get their tag ID, and we'll prompt them to basically get so their tag ID can be read. After the tag ID has been read, we then will use facial detection to be able to make sure that the guest is actually looking at our artifact. After that, we will then, and we've decided that they are actually interested in the exhibit, we will then query the database for name and language information from them. We'll then use this information to create that personalized experience. And then after we've done our presentation, the exhibit has done its finish, we'll then reset for the next guest. So to talk more about our data buffer board, I will pass it off to Karani.
Thanks, Robert. Good morning. One of the main components of our project is the data buffer. And its main function is to interface with and connect our modules so that they can exchange information very smoothly. The data buffer, we have chosen this data buffer PIC24 because of the following reasons. It has analog to digital converter inputs, and so that it receives analog input from the ultrasonic sensor, which is the range of the visitor. And also it has 2 UART channels, which allows it to send and receive information at the same time from the ultrasonics, from the RFID reader and the Raspberry Pi. And after it receives all this information, it's going to put it into data packages and send it to Raspberry Pi for further processing. And with that, I now hand over to Vieri to talk about the ultrasonic sensor.
So we said we needed an ultrasonic sensor to determine where the person is in front of the artifact. Why did we pick ultrasonic? So first of all, what is ultrasonic? these sensors send out a wave, and determining how long it takes for the wave to come back to the receiver, we can determine the distance from the artifact to the visitor. So it has a few major advantages compared to like just a motion sensor or an IR sensor, for example. So the voltage to distance correspondence is linear, which is always a good thing. And also we never have interference due to light, and we can have accurate readings throughout the whole color spectrum. So why did we pick this LV Max Sonar EZ1 MB1010? So it came right on our specs. So basically this means we have 1 inch to 7 feet of range with 1 inch accuracy, which is really good. Also, it's a low power consumption. It's always a good thing to have in a system. And we tested it against the datasheet, and we found that our outputs fit nicely on the representation that we got from the website. So our readings are really accurate. Saying that, I would like to pass on to Tim, who's going to talk a little bit more about the RFID system.
Thank you, Betty. Good morning. As has been said, we decided to incorporate an RFID system to scan the area to detect the presence of a visitor. Quick background on RFID: it stands for radio frequency identification. It's a process by which we emit an electromagnetic wave from an antenna, and then that is able to automatically detect tags in the vicinity. It emits a wave in the radio frequency spectrum, and in our case we're operating between 900 and 930 megahertz with a design center frequency at approximately 915 megahertz. And this gives us the ability to detect visitors at an approximate range of 1 meter, which is kind of our design sweet spot. But it also has the unique advantage of using passive tags. And what that means is that our tags don't require power or a battery. It's just a chip that we can adhere to a tag from a person that's energized by the wave itself, so that it cuts down on some costs and affords us some flexibility. We selected to use an RFID reader module, which communicates via UART, which is our preferred serial communication protocol. To talk more now about our antenna design, I'd like to introduce Hunter. Thank you.
Thank you, Tim. So I designed our RFID antenna. We went with a circular polarized patch antenna with a center frequency of 915 megahertz, and we were expecting to have a maximum return loss of negative 20 dB, which basically just means that how focused the antenna is going to be at that center frequency, while canceling out any other noise at the surrounding frequencies that we don't want. As you can see here in the purchase antenna that we bought to base our design off of, when we tested it, we were able to achieved negative 33 dB, which is well above the 20 dB minimum we were looking for. And it has a very wide bandwidth. The one I designed has a slightly narrower bandwidth, but was still able to achieve at the 915 megahertz center frequency, still negative 27 dB return loss. Even though it's slightly less return loss and slightly narrower bandwidth than the one we purchased, it was still able to read the tags like we wanted. And because it's circularly polarized, we can read the tag that the user is wearing at any orientation, so that in case the tag is skewed off the side or tilted, it can still be read and processed by the RFID reader. Next, I'm going to pass it off to Lizzie to talk about facial detection.
Now, to be able to determine whether or not the user is interested in our booth, we're using facial detection. The facial detection works by taking an image of the user and then going through the image block by block, looking for facial features such as eyes or noses. The result is that our camera can find a face that's 1.5 to 6 feet away with the user looking at or near the camera in less than a second. And to give feedback to the user, we're using eSpeak, which allows us to uniquely generate speech customized to the user. It works by using mnemonics to read the text and generate an audio signal. The result is that we are able to speak to the user in English or Spanish and to say their name. And to complement our use of eSpeak, we've made a graphical user interface, which is useful for the hard of hearing and deaf. And to do this, we're using TK Insert. The result is that we can display an image of the user and to display the text that we are speaking to them. Now, to speak more about the database, here's Robert.
So we wanted to implement a back-end database for ease of use so that we didn't actually have to store all the information on the users on each individual exhibits what we designed. So basically we decided to use Microsoft SQL Server 2012 running Microsoft SQL Express. In the database we are storing their name and their preferred language, and we are connecting this via a wired LAN network. We picked a wired LAN network for security and make ease of use so that it's reliable. So next, to talk about the housing, I'll pass it off to Roy.
Thank you. So we wanted to take everything that we'd done this semester and put it into an aesthetically pleasing housing that would sit alongside, the piece of art exhibit that the visitors would visit. To do that, we created a 3D printed housing. We made it stackable as far as we have removable trays for the PWB sit on. That helps us with the ease of assembly, putting it together. It's very small. It's 4 inches wide by about 8 by 8, so it's a very small footprint. It uses about 370 cubic inches of filament, so it cost about $370 if we were to actually pay for it, which we did not have to. Roll into the next slide. Budget, I like to think of that as a stretch goal. We had a budget of $750. We ended up spending $875. A large portion of that was, in the development. We had about $140 in development costs to support the software environment. We had to pick up a couple of development kits for the microprocessor or microcontrollers. The calculated per unit cost would be $361, and obviously that doesn't include the freebies that we got at SCSU, like the circuit boards and the housing. Some of the big lessons learned in the last 4 months is we spent a little bit too long in the conceptualization phase and got a late start in actual development work. We, in retrospect, should have started development probably week 2. We didn't quite finish our specification and design until week 3. We also succumbed to a little bit of feature creep. We had a lot of grand ideas about what this project would do at the end, and ultimately 4 months is not enough time to get a lot of that done. The facial detection was one of our successes, as was the overall system integration. It was a lot of pieces coming together, and as of last night, they all came together quite nicely. We have a working project. Some of the things that we would like to improve if we had more time, or next iteration would be the antenna range. We were shooting for a 3 to 5 foot antenna range, and we fell short. We understand why that is. We just don't have enough time to respin the PWB and do another antenna. And one of the primary goals that we had in the beginning was to be able to handle multiple visitors coming to the site. How do we handle if 3 people are all at the same artifact? What information do we display on the monitor? We just ran out of time to handle that collision detection. So right now we only support, one person at a time. It would be another 2 weeks of effort to hammer out the collision handling. Here's a demonstration of our, bouncing around on me. So here's a demonstration of how the system works. Obviously this is our housing here. That's the RFID tag. It's going to get detected by the monitor back there, and when it detects it, it's going to then do a facial scan for the facial detection, and then it will display the information that we want to display on the monitor back. And thank you for listening to our presentation. And we appreciate any feedback or comments.